Should we get recording? Okay. Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Our distinguished speaker today is Dr. RahulMangharam. And Dr. Rahul builds as safe autonomous systems to the intersection of formal methods, machine learning, and controls. He applies his work to safety-critical autonomous vehicles, urban air mobility, life-critical medical devices, and AI co-designers for complex systems. He is the Penn Director for Department of Transportation's $20 million Safety21 National UTC, which focuses on technologies for safe and efficient movement of people and goods. Rahul is the Director of the Autoware Center of Excellence for Autonomous Driving, a consortium of 70+ companies and universities focused on open source AV software for open standards AV platforms. Dr. Rahul received the 2016 US Presidential Early Career Award, PECASE, from President Obama for his work on life-critical systems. He also received the 2016 Department of Energy's CleanTech Prize Regional, the 2014 IEEE Benjamin Franklin Key Award, and 2013 NSF CAREER Award, and 2012 Intel Early Career Award. He was selected by National Academy of Engineering for the 2012 and 2017 US Frontier of Engineering. He has won several ACM and IEEE Best Paper Awards in cyber physical systems, controls, machine learning, and education. Dr. Rahul, it's a great honor to have you as part of the webinar series at UND. And the floor is yours, and we look forward to your presentation. And thank you so much for taking the time to do this webinar series.
Thank you so much, Professor Ranganathan. It's my pleasure to talk to your group here at UND, and hopefully you guys find this interesting. So over the next 45, 50 minutes, we're going to make it very exciting. We're going to talk about some really interesting topics that are basically when software is at the level of making life and death decisions on our behalf. A lot of my lab is focused on how do we ensure that that software actually keeps the humans safe. So for example, our research, we call our lab X Lab, and we are very general in the sense that we are really solving, we don't have just a fixed set of tools, but we are really finding interesting problems to solve. And then we spend, over a decade on each problem. And so most of the work over here, it's at the intersection of, formal methods. So essentially we are trying to, we have to build models, mathematical models that can that can model the interaction, say, between the device and the human, whether the device is like an implantable medical device or the device is like a self-driving autonomous car that is making decisions on our behalf. And the human is interacting with that, or the device is within the human. So we have to build these mathematical models where we can then prove, not just by testing, but through verification, that under all possible conditions, the device will not push the human into an adverse or an unsafe condition. And mostly these interactions between the device and the physical system, whether it's a car, whether it's a medical device, whether it's a building and the controllers in it, they all have a closed control loop, and that well specifies the interaction between those two. And we have built a lot of machine learning in our tools under the hood to be able to capture these complex models, to then be able to have learning-based control or learning-based verification and to work in that manner. So no matter what problem we work on, we ask the same question, how can we provide safety and performance guarantees for these closed loop life critical systems? So I work in like 3 different domains. So there is medical devices. I'll briefly talk about that just to give you a flavor of what we mean by life critical systems. But mostly we'll talk about autonomous systems research today, and we'll keep energy systems for another time. So in medical devices, like suppose you have a device like a pacemaker, or that is, if your heart is beating too slow, then these devices will speed up your heart. They will pace the heart with an electric pulse, and they will speed up the rhythm of the heart electrically. Or if your heart has derangements and it is like it's beating too fast, then what you see in the movies, like in Scrubs or in different medical dramas on TV, they basically are taking a defibrillator, external defibrillator, and cardioverting the patient, essentially resetting the heart by shocking, providing a large electric pulse to the heart. And so those devices are implanted. So essentially the physicians make a cut in the chest over here, and then they put the device in, and then they loop these catheters, as you can see in the image here, into the atrium. So one goes into the top of the heart, and then the other one goes into the ventricle. And they're sensing the heart. If the heart basically starts to beat, very fast or very erratically, then the device has a supercapacitor, it charges up, and then it provides a big bang. And this is like a 61 joule or 800 volt shock to the heart, and then it basically is rebooting the heart, so to speak. The question is that there's a lot of software now running in these devices for sensing, for discriminating between different types of signals that are coming in, and deciding whether it should shock or not shock the heart, or apply some other kind of rhythm therapy. So these devices on the whole, they extend human life by an average of at least 6 years. But in the past 2 decades, they found that these devices actually have a lot of recalls due to software issues. And so our focus has been on, like, how do we now have this, define and understand the logic of the software in reaction to the hearts. And your heart is different from mine. My heart is different before a coffee, after a coffee. And so our question was, okay, we need to model the physiological system. We need to model the electrical system and the decision-making system in these devices, and then look at this closed loop interaction. So over the years, we found that, say in the 90s, 10% of all recalls were due to software-related issues. And then in the following, like the last decade, 15%, the largest share of medical device recalls are due to software. And this is across class 1, 2, and 3 devices, which are basically like implantable, life-critical devices to even wearables that are like not just providing, devices that are providing diagnosis and therapy, and devices that are only providing diagnosis. So with these kind of devices, mostly people are testing them. They're running many tests. So these are called tape tests. They just look at like boundary scenarios. When will the device trigger? Should it trigger? But these tests are not sufficient. Actually, because, as I mentioned, your heart is different from mine. They actually want to be testing it out with a real heart, but you can do that only for very few hearts. And so over the years, we wanted to build this sort of system where we can have a closed loop testing and verification system. And we enabled like our heart on a chip modules to be able to do this kind of evaluation of these devices. And so this is like our previous research. So between like, say, 2010 to about 2020, so we had about a decade of this work, where we built these very abstract but mathematical models of the heart and of the device, and then we could verify them. What verification means is that it is exhaustively evaluating all possible states and all possible interactions between these two, and telling us that, well, this is going to be safe under all these conditions. And then from that means we know that the logic of the device is good, and it works for a very large class of possible signals that could come out of the heart. And then we can generate from that an actual instance of the code in software to do testing. And then this testing is sort of guided testing. That means we are guiding the test to find these unsafe operations and to root them out. So there's like almost like a gradient descent guiding the test towards a falsification of the device. So making sure that this particular instance of the code, and then we can generate actual code that goes onto the device and onto the heart models, and then actually run physical level testing with actual electrical signals. And so in the early days, we had built these kind of very, high level heart models. By high level, I mean, it's really just looking at the electrical conduction from a device's perspective. We don't have to model the entire dynamics of the muscles and the tissue and the blood flow, because the device only has 2 leads into the heart. It cannot see the global, activity of the electrical activity of the heart. The other thing is we are only taking an electrical activity view of the heart. And we're not interested, in say the valves or, blockages in the valves. It's really just the electricity that is passing through the heart creates this frontier. And that's what's causing our natural rhythm. And when there are derangements or, any sort of corruption in this rhythm, that's what's called an arrhythmia. And there are slow heartbeats, there are fast heartbeats, there are irregular heartbeats. And so we look at all of these type of arrhythmias within this kind of, verification and testing. And then from that, we progressed on to like modeling more complex behavior, like what is called atrial fibrillation. So atrial fibrillation is essentially a very chaotic condition where the heart's normal rhythm that just goes like say dup 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 dup. It's just like that you have a heartbeat. Here, this is like you have many where in the normal heartbeat you have like a single source that triggers the heart to then have this rhythmic behavior, a regular behavior. And with atrial fibrillation, it's a much more chaotic behavior because random places in the heart tissue are triggering, providing their own sources of trigger. So now the heart is, in a very chaotic, like almost like fireworks are happening, but in a non-repeatable fashion. So what the physician has to then do is they put a catheter right from your leg, goes up the vein into the heart. And this is an example of the catheter over here. It's called a Penn Director catheter with 5 fingers. And then they basically now capture the geometry of the heart by probing the heart. And then they capture what is called over here a conduction map, like how well is the tissue conducting and capturing the dipoles essentially of the heart. And so what we then do is we can export that 3D physical model of the heart and the conduction by this sampling, and we can now generate this heart model as a computational heart model, run many simulations that are very patient and tune the heart to be patient specific. And then we can guide the physician to say, okay, because the physician is trying to say, where are these spurious signals coming from? And then they take a different catheter and that's called an ablation catheter, and they go and burn the tissue. They kill the cells so that these spurious triggers stop happening. So it's almost like a search and destroy mission, but it's very difficult for the physician to find out because they cannot visualize, what is happening globally in the heart. They can just see these electrical signals that are streaming by. It's kind of like Neo in the Matrix. It's just looking at this code, and then they say, they're mapping what is happening temporally into the spatial aspect. And so essentially we model the heart, with this electrophysiological models over here, and these are like these there are different levels to model the heart, but we are modeling the tissue and the conduction and the propagation of the waves at every walk cell over here, and then how it is connected to the entire mesh. And then we can tune this, the behavior of how this particular patient's heart is conducting at different locations. And we can do a global tuning so that when we then test it out, we can actually map out exactly where the tissue is conducting well and where there is scar. Scar is basically dead cell that does not conduct. And scar creates a lot of these anomalies in the timing. And so now we can classify, the conduction across the heart. And then what we can do is we can then model very complex behavior, like these traversal of these waves as it's propagating across, whether it is scar tissue that doesn't conduct, or traversal of like rotors. These are like chaotic behaviors that spontaneously generate, and then they persist, and then they spontaneously also terminate. But these give us a clue as to where these spurious behaviors are triggering from. And so now we can give the physician like a heat map to guide them to say, don't waste your time, because these procedures take like, anywhere from 4 to 7 hours, and the patient has to be awake because they burn the tissue, then they have to put the patient back into atrial fibrillation, see if it persists. Otherwise, they have to cardiovert the patient, shock the patient again, and then go and burn the tissue again and keep repeating that. And so it's obviously a very, tiresome and painful procedure. There's no blood involved outside of the body, but it's a long and, arduous procedure. but it's also that 70% of the cases the physicians can solve, but the remaining 30% they don't know how to. So we want to basically make the invisible visible for the physician, and we ran these as small scale clinical trials with about 15 patients, and we could show that we have about 97% accuracy in terms of spatiotemporal behavior of the patient and our heart model that is generated in near real time, and that provides that. The next level was to say, okay, how can we now run this for large scale clinical trials, which take many years, several million, and over 35% of these trials fail. And so the idea is that can we use our synthetic heart models and our device models as virtual basically models that can have regulatory grade evidence to be considered within a clinical trial. So suppose a clinical trial has 2,200 patients. The problem is that many patients will die. Many patients will actually just leave the trial. They'll be non-compliant, and there's this attrition that causes the trial to fail. So can we say replace 200 of the control arm of a clinical trial with say 11,000 patients? So we built this statistical framework to model how the uncertainty goes through these devices, through our models themselves. Because simulation land is simulation. How good is it? For modeling a real patient, we need to get real with that, right? We are not trying to say our simulation is as good as a real patient, but we can say this is where the uncertainty is. This is the quantified uncertainty, and then subject or conditioned on that uncertainty. This is why we have to replace 200 patients with 11,000 of our virtual patients. And so essentially building this statistical framework so that now when they do clinical trials in the future, we can also run the trial prior to the clinical trial to see an outcome. So for example, we can do this replacement over here, or we can actually, also post-trial, we can actually evaluate how robust was the outcome of the trial. Like, was it sensitive just to that population or not sensitive enough? So for example, in between 2006 to 2011, there was a company called Boston Scientific, or Guidant at that time. They said their defibrillator is 25% better at discriminating whether they should shock the patient or not shock the patient, and than say Medtronic. And so they did the trial, and what happened was that it actually showed that not only were they shocking the patient inappropriately 62% of the time. That means you get one shock, you get another shock for free, and you don't want that free shock in this case. And they were 34% worse than Medtronic. Now, I don't care about which company is which. I don't have stock in either company, but the idea here is that we did this computer-aided clinical trial prior to with the data that they had prior to the trial, and we could show that the outcome would be very similar to the outcome of the trial. We can't get the exact numbers, but we can show the direction of the trial. That the direction of the trial was that this company A was actually worse than company B by a significant proportion. They shouldn't have gone ahead with that trial, right? If they wanted to prove that point. So we can also show when we run the trial with our virtual models, these computer-aided clinical trial models, where we have high confidence, say with more rhythmic, like regular rhythms, and where we have low confidence with more chaotic rhythms. So then we can kind of guide the trial to have more patients that our virtual patients are not able to model as well, and less patients where we can model with very high accuracy. And so this was a NSF Cyber Physical Systems Frontier project that just ended. But it was a really great collaboration with, cardiologists, physicists, bioengineering people, computer scientists. I was the one electrical engineer, and it was called Cybercardia. And through that, we had, just my team alone had 26 students. And then many of them became professors from just this part of the lab. And then many went to grad school after that, and it was a really fun project and there was a lot of learning because we had to learn the clinical side, the biology side, and all of this is captured in the medcps.org website, and you can see all the papers and all the code and everything is available there. So that's just the appetizer. It took a little bit longer than I expected, but let's get on to the main course of autonomous systems. So, so you obviously have seen a lot of these self-driving cars out there. I'm not going to talk about like, oh, let's build the next self-driving car. I'm going to talk about what can we learn from that to build the future autonomous systems, not just autonomous vehicles, like that, right? So how do we build superhuman capabilities into our autonomous systems that can still be very safe? So I'll just skip over this intro. Let's go into the main topic over here. So we call this MAD games or multi-agent dynamic games, but with autonomous racing. Now you might think autonomous racing, that sounds like a little, childish, or, it sounds like it's a good hobby. Why are we doing this for research? Let me give you some, motivation. So you see in these kind of scenarios, right? When you're trying to merge on a highway, say in this case, this yellow truck is not allowing this car to merge over here. But eventually, we get across. We nudge, 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 and people get across like that, right? So here the goal is to be, as safe as possible. But autonomous vehicles, in this kind of non-cooperative scenarios, they still struggle a lot. And but in civilian driving, your goal is to just get home or get to the office or wherever you're going. And if you're 3-4 minutes late, no problem. At least you're alive. Nobody even says that, right? I mean, but so safety is maximized in civilian driving, but performance is not even specified over there like that, right? They could. So, but that's why we look at racing, where here, these vehicles are driving at over, 300 kilometers per hour and very high speeds, very close to each other, very risky maneuvers. And they get penalized if they are too conservative, too slow, they're out of the race, or too fast, they crash, they're out of the race. In fact, if you're just half a second too slow, you're out of the top 10 in any F1 race like that, right? So the penalty of being too conservative or even slightly conservative is drastic over here. That's a career choice, right? In fact, nobody wants to make that choice because that's what their career is to race. But it's not all about being, the fastest possible driver. In fact, between 1950 to 2022, the winners of F1 Grand Prix, only 40% of the time the winners were the fastest cars. The key point that they were good at was in balancing, aggressiveness and restraint throughout the race. When to be more aggressive, when to have restraint, when to, try to be more safe, and keep balancing that and making that decision at the right time. And that's what we are trying to learn when we observe other drivers. But here, these vehicles are, operating at the limits of their handling, right? So they're operating at their dynamic limits. That's why we have MAD, the D in MAD games, multi-agent dynamic games. The dynamic part is that they're operating at the nonlinear knee of their tires. They're operating at the full throttle of their engines, and they are drifting. They have a very high wheel slip. And because if you're not operating at the limits of your handling, your opponents are, and then they will win, right? So high speeds, high accelerations, small reaction times, and full vehicle dynamics are required over here. Obviously, crashing is expensive and dangerous. The thing is that our sensors like LiDARs, cameras, radars, they tell you where the other vehicle is. They tell you the pose of the other vehicle. And maybe you can predict, in a short term where the other vehicle is going. But what we really want to know is what's in the opponent's mind. What is their intention? What is their driving policy? So the policy means that, if we were to train like a neural network, for example, the policy would be like, what is their behavior going to be at the next turn? How are they going to behave in this type of interaction? So we are really looking at that overall behavior. That's what we want to find, but our sensors are not going to give us that. But that's the goal for the next couple of slides. Now you might say, okay, why don't you just look at the last 10 years? You have data from 1955, look at that, and just do supervised learning. The problem is that every race is unique. The cars are different, the track conditions are different, and even the driver's mindset is different. So we can't really glean too much from the previous races, even though the tracks are the same. And so we basically are operating in a small data regime. That basically means that we don't know much about the strategy the other agents are going to use in this competition. And that's what brings us to our motivation, is that we want to develop these superhuman drivers that can then, through being super agile, can bring us safety, and they can help us like outmaneuver in ourselves in risky situations. But we want to learn how to train these autonomous systems to be better than humans. And so the first question then is, so how do we generate the most competitive agents who can dynamically balance safety and assertiveness? And that's what we did in this ICML paper called Formula Zero. You know what Formula 1 is, but Formula 0 is saying that, oh, I don't know anything about my opponents, but I still want to learn online what my opponent is like, what their behavior is like, what is their driving policy, and then I can outmaneuver them during the race. Okay, but before the race, I don't know anything about you as my opponent over here. So we model this problem, we formulate this as a robust reinforcement learning problem, where our goal is to minimize, an expected cost over a set of actions over time. But the problem is that we are not just operating alone. If I was just operating alone, I would just use this formulation and come up with a minimum cost trajectory that follows a racing line, and then I can race as fast as possible. But I'm operating in an environment with other agents, but I don't know how the other agents are. I have this uncertainty. So then we model this as a mini max problem over a set of transition probabilities over a set of state and action transitions, which we call PSA. And our goal is basically we can only partially observe the other agents. And so by making many partial observations of the other agent, I want to learn what that behavior is. And so we model this as a POM-DP, or a partially observable Markov decision process. And then we use robust reinforcement learning to capture this. And what we really want to do is we want to basically parameterize this uncertainty set about the opponent. Like, what is the opponent's state and what is their next action? What is their state? What's their next action? And I want to sort of parameterize that. I just don't want to know what's their next steering angle and their acceleration or the throttle level. I want to know what is their decision making in that, right? So what we do then is, first, offline, we basically use what is called population synthesis. We use self-play. That means I don't know how to model my opponent yet, but I just generate a lot of competent opponents, and I'll show you how we do that. And basically, I can come up with, like, say, a set of 20 good racers. And so I have 20 different racing policies. And online, I use what is called a robust belief space planning. And I say, okay, I'm observing the opponent. Can this opponent be modeled as a mix of some of these 20 prototype agents, that policies that I have? So we'll come to that. That's just the overview. So essentially here, the idea is, we don't want to just model like what is the steering angle and just a short-term prediction of what they're going to do. We want to model the actual policy of the opponent and how are they going to race now over time with that, right? So the way we do this is that we want to first we want to generate a set of elite agents. And so we run this through what is called like an optimization. You can call this like a search engine, which uses self-play. That means it's just generating agents that then compete against other agents. And then the one that wins, they get promoted. And then we keep having hundreds of thousands of competitions on the track with our own agents. And then we basically keep improving their behavior by running consecutive, competitions. And then out of this search engine for generating, these and optimizing, the elite agents, we say we generate about 20, or it could be 100 other agents, but let's say we have 20 elite agents, but they also have to be very diverse. That means they have to not necessarily take the same race line. You can see they have different race lines, but they are elite in the sense that they are in the, say, 95 percentile of lap times. That means they have very low lap times. Also, when they interact with other agents, they don't always say take the inside to overtake. They have many different ways to overtake. And so they are not only elite, but they're also diverse. And that's exactly what we want. So now I have 20 elite and very diverse prototype agents, and I'm ready to go into a race. And so when I go into the race, my vehicle, this is called the ego vehicle, the red one, is basically using what is called a sampling-based planner. It is just saying, okay, I'm sampling ahead and I'm finding out what are possible trajectories that I can take to move ahead. Then I'm estimating now what is the trajectory of my opponent. I will come into the detail of that, how we estimate the trajectory of the opponent. But let's say I can estimate that opponent, then I'm going to pick out of these black trajectories the one with the lowest cost over here. And so the way we do this is by modeling this, as a belief vector of what the opponent is, their behavior is like. Say, for example, I just have 3 opponent prototype models, opponent model 1, 2, and 3. And say initially, this is me, the ego vehicle, and this is the opponent. I just say, let's say that this opponent behaves like opponent model 1. They would have taken this trajectory. If they behave like opponent model 2, they would have taken this trajectory. Or if they behave like opponent model 3, they would have taken this trajectory. And so they could have taken any one of these trajectories, but actually they take some trajectory that's slightly different. And so, but we then can start to map what the difference is, and we can treat the opponent as a weighted mixture of my 3 opponent model types over here. But I still have some uncertainty, I have some error, even with that weighted mixture, because they're not a perfect fit. So I have this uncertainty ball over here, and that's what is called distributionally robust over here. That is basically saying I'm taking into account this ambiguity or this uncertainty, and I'm modeling this opponent as a weighted mix of my prototype policies. And so essentially there, I can basically generate this minimum. I want to generate this minimum cost trajectory, knowing that my opponent is going to do a certain set of actions going into the future. And so as I'm observing the opponent model is slightly shifting also over time, and we are updating our estimate of what the opponent's policy is like, given our offline prototype policies of the opponent. Right, so we don't know which one it is exactly, but we are now estimating, okay, you could be a mix of this. So another way to say is that in the beginning of the race, I have, say, 6 prototype policies, over here. And then as I observe the opponent in about 150 to 250 observations running at 10 hertz. So very quickly, I can then figure out that, oh, it's mostly heavily weighted with opponent model 5, and then the other opponent models are, have smaller weights like that, right? And so now I can model my opponent as given these offline generated policies. What does that help me do, right? So that helps me now say, okay, well, I can bound and minimize the uncertainty of how my opponent is going to behave, and learn how the opponent is going to behave, and then outperform them or outcompete them through the race. And so the first question was, how do we now, if we become more conservative, we want to sort of spend less time in this very small time to collision regime. That means I don't want to be in a near accident situation. So the more robustness I have, the more distance I'm keeping from the opponent. I'm not allowing myself to come very close to the opponent. The more uncertainty I have, the less time I spend in this risky zone of less than 5 seconds to crash with the opponent over here. So time to collision is basically saying, what's the time for me to hit the opponent? I don't want to be in a very small time to hit the opponent. So this is just saying that the more robustness we have, the less time we spend in this near accident situation. But the problem is that the more conservative I get, my win rate over here goes down from about 60% to 50%. And that is not acceptable. So I don't want to sacrifice, my winning. So what we showed with our work is that, when we have this adaptation, we can basically regain the loss in the win rate, and basically maintain a high win rate even with high robustness, because now as we are driving, initially we don't know much about the opponent, and as we're driving, we learn a lot more about the opponent, and then we can drive very aggressively but also be very safe in and around them, because I have a really good estimate of how you are going to behave. And then I can drive aggressively to outcompete you, but still not crash. So that's the whole point of this approach. So whatever we do in the applied theory, we also actually directly apply it to our scaled vehicles. So here, this is now learning the behavior of the opponent based on these prototype models. And then it is coming up with, overtaking strategies. So the car in the rear is basically our ego vehicle. And then in simulation, it's about 150 to 250 observations. And then we can get a good fix on the opponent's policy. In reality, because of the field of view and the noise with the LiDAR, it's about 600 to 700 observations that are required, but still running at 10 Hertz. We were just able to show that, we can run this entire machine learning pipeline on board on these vehicles. So this first part basically showed that, we can, synthesize first offline a diverse population of high performing policies. And then online, we can use this, distributionally robust planning and do this adaptation to basically outcompete, the opponent, but while remaining safe. So following that, I'll skip through some of the future slides. I don't want to take up too much time. We've modeled this in a game theoretic perspective. So what is a continuous game like that, right? So most games that we see, like, poker or Go or chess, they're all discrete games. But now when we move to like this continuous motion planning, we have a big problem, because, suppose here let me set up the problem first and I'll tell you what issues we have. So here, the ego is in orange and the green vehicle is the opponent. In the beginning, first of all, I have imperfect information. I know nothing about my opponent, but I have perfect recall. That means as we are racing, I just record everything the opponent is doing when I'm close to them, when I'm interacting with them, when they are near the turn of the track. How do they behave? And then at some point in the future, I say, okay, I have observed my opponent, and now I need to make a decision on how I need to change my, driving policy to some other policy so I can outcompete them. So I'm basically now not just, doing motion planning. I'm actually saying, okay, I need to choose a different planning policy so that I can change my behavior to then say maybe become more aggressive and outcompete them. So this is called an extensive game. So it's a sequential decision-making game. So essentially, but I have multiple chances. I can make a decision here. I can make a decision. Eventually, I want to basically outcompete them. So here, but the problem with motion planning is that it is, it's the state space, the action space, the control space, the observation space is all infinitely large. And so we need to reduce this problem to something like, in this 2D. So what we did for this research was to reduce this very complex problem into just a 2D decision-making plane where I observe the opponent's policy on, a scale of aggressiveness and restraint. And then at this decision point, I decide to say, in a more simple case, decide to become more aggressive. So then I change my policy and I can outcompete them and overtake them. Maybe I don't overtake them right away, but eventually I can keep making decisions in response to the observed policy. So now we have taken this sort of problem to one level above, is mostly like on racing strategy. So how can we come up with that, right? So I have not explained to you how we came up with this part, but that was the whole point of the research. So as I mentioned, the planning space is infinitely large. So what when you're planning, you have the sampling-based planners, for example, they're finding feasible trajectories. You need to encourage high speeds or penalize co-occurrence of high speeds, high curvature, not crash into the other vehicles, try to remain on the racing line. So motion planning has many costs involved in it. And so we run this for like hundreds of thousands of interactions between these vehicles. And we parameterize the motion planner to say, okay, well, these are the weights for these different costs. Which ones won in this situation? Which ones didn't win these situations? And then we generate a set of elite policies, but on this scale of aggressiveness and conservativeness. And essentially, we are just parameterizing it, but we're reducing our very large dimensional problem to just a 2D or a reduced dimensionality, have a dimensionality reduction to just this sort of scale over here. And the way we do this is by, again, running, this kind of gradient-free optimization of many competitions together. And we have these elite policies now, but we are putting this within a game theoretic framework, unlike previously, where we were mostly just in the motion planning frame of reference. Here we run what is called a counterfactual regret minimization. It's basically saying, okay, which policy should I pick next? What is the best policy to pick in response to the opponent now? What is the best one? So to run this counterfactual regret minimization online is very time consuming. So we actually just learn an approximation of this game by running this game for millions of iterations or millions of trials. And we basically figure out what is the best policy switching strategy to run online. And then we run our races. As we are observing the opponent over here, we observe, and then we identify what policy they have. Then we decide to have a new switch to a different policy. And then we can become, say, more aggressive in this case and overtake the opponent like that, right? So for example, in this example, we observe the opponent and then we become more aggressive. So what we are able to show, I'm skipping around the details of how we did this, but we are able to show with high statistical significance that game theoretic motion planning actually significantly outperforms non-game theoretic motion planning, like from a 51% win rate to a 57% win rate. But it also generalizes very well to unseen opponents and to unseen maps. So it's both high performance and very generalizable. And so it's not always we become more aggressive. If the opponent is here, we become more and more and more aggressive till we win. Sometimes if the opponent is very aggressive, then we have to become less aggressive because we don't want to crash and later on become more aggressive. So it's not all about like being more macho. It's being, it's really balancing safety and then performance in this case, right? So if you are too aggressive and I'm too aggressive, then that's not good for us, like that, right? So I'll skip over the rest of this, but I just want to show you some other topics that we work on. So this is actually an older slide of our research group that works just on autonomy. This group has now doubled in size since the last 2 years. It's a very fun group, lots of diversity over here, many different people from many different countries. It's a very fun lab. And a lot of our focus is on also like, how do we build the next electric vehicles? And how do we then, so this is a different project. Sorry, I think slides got slipped out, but yeah. All right, so let me just. So another problem that we work on is now, how do we if we want to make a new design of a system, rather than start from scratch or just reuse the old libraries, can we mine the previous designs to generate, partially complete new designs for new requirements? So essentially, if I want to make drones and I have made, say, many different drones in the previous case that maybe they were just monitoring power lines or they were just doing some tracking. Now I want to make a pursuit avoid drone or a leader follower drone. So can I use the previous drone designs of the electrical, mechanical, power, software, aviation, autonomy, perception planning, control pipelines, capture them in this knowledge graph. And then when I have a new requirement to say, make a leader follower drone now, can I have an automatic pipeline that comes up with new designs, generates new designs, and then creates like, low fidelity designs, evaluates them, and then keeps going through this process of generating better and better designs till we have detailed designs, and then we can evaluate them for these different constraints. And then we obviously have the human to sort of tweak this. So here, this is like, can we have this generative design for the entire, autonomy pipeline, but including the mechanical, electrical, and the whole system wide. So we did this for drones, for example, where we had some seed designs that were handmade, and we could generate many feasible and dynamically feasible designs that would also fly. I won't say they would fly very well, but some fly better than others. And they are very funky designs, but they all are legal in the sense that in the simulator, they work well. So then we had many sort of prototypes, like, how far can it fly? So then this design was generated to see that it has more rotors, more batteries, so it can fly very far. So that's the benchmark, and automatically comes up with a design that then can win that benchmark. Or another one was, how well can it fly in a circle? Here you can, so if it's going around in a circle, here you can see these rotors are equally sized, but this one on the inside is smaller because it's doing less work. So it's actually optimized for the benchmark. And so it's coming up with all these designs for different benchmarks. And we had won this sort of competition of generative design for, say, drones. So essentially, we want to do this for cars, we want to do this for drones, for many different systems, go through this pipeline of architectural space exploration and then parametric optimization and coming up with new designs automatically, or at least doing like how you have autocomplete with Google. If you give it a 50% complete design, it can take it to 80% completion with 80% success, and then you can finish the last part of the design. The other questions are, how do we build the most efficient autonomous race car? Can we have this like multi-domain optimization across the mechanical, across the control, across the decision? So many different aspects of the vehicle need to be optimized. So say in this case, the lap time is, if I just tweak it by hand, I have like, the mechanical aspects, the path planning, the control, and the lap time is 25 seconds. Now, if I keep tweaking it manually, it can come down to the limit here. The vehicle is drifting, I can't go any faster, and the lap time is down to 15 seconds. But the question is, can we now automatically do this? And that's why we built this tool called Tuner Car to do the super optimization or multi-domain optimization across mechanical control and planning and decision making for the vehicle to come up with that. Because we want to say, okay, look, cars will change, racetracks will change, but we want to have a reusable core autonomy software stack. So how can we now optimize this stack every time the vehicle changes or the environment changes? And we also want to obviously run it on our small scale vehicles to show that it actually works. And so we built this pipeline now to do this multi-domain optimization. I won't go into the details of it, but essentially this is kind of like, given a track, it'll actually give us this race line. It'll automatically generate this race line. And what we see on the Z-axis is the wheel slip over here. And so essentially, normally, like if we see at this turn, normally a car will follow this dotted line to go to the apex, and it would come in fast, brake, and then speed up. But in our case, because we know the vehicle dynamics, we optimize for this, and the car comes in really fast, still stays really fast, drifts through the corner, and then speeds up. It does, and like the normal race line doesn't call for drifting. Here, the vehicle is drifting at all these corners. So we are really pushing the limits. And whatever we do, in our simulation land over here, we do it for real. And so we can generate, the actual race line for this vehicle, for this map. And it works really well. There is obviously a sim to real gap. And other problems are like, I'm just going to mention the problems now because there's not much time. But other problems are like, when we do localization for robots, normally we use iterative algorithms like particle filters. But here we use an approach called normalizing flows or invertible neural networks, where we can capture from LiDAR scans, we can estimate the pose with high accuracy, and it's very efficient. So we can run it at over 270 Hertz. And so this is using invertible neural networks to localize the vehicles with LiDARs and also with radars. Not radars, but also with cameras. So for example, if you're driving through the corridor, actually none of these images are part of the original data set. These images are all generated from the invertible neural network, just to show that it can also generate images and it can also localize. This is obviously a very interesting topic. I'm not giving it justice, but it's just to show that we can do learning-based localization, learning-based planning, learning-based control. And that's what the remaining set of slides are on. Like here, there is learning-based control. If you have multiple frictions, how can we learn how to optimize the model predictive controller in a data-driven manner so that it retunes and the vehicle still remains, in control as the frictions are going from high friction to very slippery, low friction. And then as the frictions are changing, the vehicle is tracking really well like that, right? So in the last, 5 minutes, I want to just take, and then I'll wrap up. I'll just talk about some of the external, like, outreach activities that we do overall, right? So we have this large community of over 80 universities that are part of this F110th autonomous racing program. And the whole idea was, to build an autonomous system, you need a lot of different skills. And then when you go into, say, the industry, you just, you learn one subject at a time, like signal processing or computer vision or linear algebra. But when you're building a real system, you need to treat it as a system. And then you need to then be able to debug it and as a system, optimize it as a system. So F110th really allows for that type of education. And so essentially it's bringing in together perception, planning, control, but in a very exciting, environment of racing. And so this is like a standard, like a powerful RC car. And, but it's actually the software and the decision making that is very complex in this. And that's all running on this GPU board over here. It has LiDARs, cameras, IMUs, and so on. So it's complex, but not too complex, like you would say if you joined like, Toyota or some big, or you joined Boeing and you're working on very complex systems. But there you are like in a subdivisions, division, and you're just testing like a driver for something. You're just working on a very small subcomponent. Here you get to work on the whole system. So we call it because it's F110, because it's 1/10 the size, but it's 10 times the fun because you can do it. You can drive it, you can race it, you can crash it, but you build the perception planning control pipeline. To aid with that, we have simulators, 2D simulators for motion planning and control, 3D simulators for perception. And we help the community build code and race. But it's not just doing simple, like, object avoidance. We run SLAM over the past 5 years. SLAM has been running like simultaneous localization and mapping very efficiently, builds the maps, and then figures out how to drive in a map. Instead of just simple, like, wall following algorithms, here we run all the modern, sampling-based planners, motion planning algorithms, like rapidly exploding random trees that are optimized for, this motion planning. And instead of just learning PID control, you learn about model predictive control, and that works flawlessly on this platform also. In fact, this is a race from 2019, and it's showing model predictive control in action. And so it's a great platform to learn a lot of these advanced topics for autonomous systems. We have an entire course on the f110th.org website, and there are no exams, just races, but all the lectures, all the simulations, all the labs, the code, everything is available for free online. Thousands of students have followed this, and many come to race. Many projects are done every semester on these, and those are also available as references if you're looking for, like, a thesis project or an independent study project. A lot of the students involved in this have grown through, and they've become leaders in Tesla. In fact, this student over here, he was in Tesla for about 6-7 years as a leader for motion planning. And now he just is a co-founder of a $150 million company called Bot Company, I think, that just got launched last week. So, but the idea is that, it helps you, not just get a job, but also like take you on a really good career trajectory. Everything is available on this website. We have many competitions. And this year, in fact, we have 7 competitions. I just came back from Japan, where we had a very large competition like this ICRA one, but ICRA 2024. I should update the slides, but and then next week we will have another one in Korea. We had another one in Hong Kong, but all as part of big conferences. And you can see everyone brings the cars. They build the cars. They are just based on the reference design. Same vehicle can't have faster motors, can't have better sensors. It's a battle of algorithms. And you can see people are very happy here. This is how the races happen. ET at Zurich is in the lead.
Your team is still struggling with the pressure made up by
and lots of people come and watch the races. It's really, really fun. It's very nerve-wracking. It looks like it's slow from this perspective, but the students are building a map. They're coming up with their race lines, and then they're racing along that. Then they have to come up with their overtaking strategies. And again, this has just been growing and growing over the years. This is in ICRA 23 in London, and people from all over the world have come. And these are very exciting. This was in Detroit last October. You can see how agile the vehicles are becoming over time, and sort of like many people have developed tutorial videos. This is just showing what's happening under the hood. I'll skip over this video, but I'll share my slides with the organizers, and there are many viral videos. This one has over 600K views. That the students developing them develop this, right? So many future, like as I mentioned, 7 autonomous racing competitions this year, many sort of workshops. I just want to wrap up with showing what we also are developing with Autoware, which is the world's leading autonomous software, open source software stack that runs on many different types of vehicles. So I serve as the member of the board of the Autoware Foundation, and I also lead the Autoware Center of Excellence. So the Autoware Foundation has over 70 industry and academic and government members, including big companies like ARM, for example. Through that, we have many collaborators now, across the world, who are all using Autoware on research vehicles that they have. And these are all folks across the world, and we are developing essentially the next generation of open source AV software for open electric vehicle platforms. And we run Autoware on our 1/10 scale vehicles, on autonomous go-karts, and then on full scale vehicles. The same software is running across all these platforms. So we built these autonomous racing cars. This is electric and drive-by-wire, steer-by-wire, brake-by-wire. It's all done by master students in 5 months. And everything is open sourced. All the designs are available in av4ev.org. This is the team. That's, again, a very diverse team. It's a fully student-driven project, and we have our real build environment. And this is the simulation of that. So we can actually test out the vehicle, and the simulator is built for the go-kart. So they also won the competition last year in Purdue, and actually today is the competition in Purdue again this year. So we'll see how they do. But the team is, I think it's it's a really good opportunity for students to learn. So I'll wrap up at this point. I think learning from racing in terms of multi-agent strategies or learning-based perception, planning, control algorithms, and then being able to implement them with real platforms, whether small scale like F110 or mid scale like the go-kart or full scale like the Autoware vehicles, is a great pipeline to going from learning concepts and learning the analytical math and the coding to actually really becoming a full stack engineer and a platform architect. So I'll stop at this point, and I'm happy to take any questions.
Thank you so much, Dr. Rahul, for the fascinating presentation. I think you touched a lot of information in a short amount of time, but we'll open up Q&A right now, and I'll see what questions coming in. Maybe I'll start with the first question while the questions are coming in. The one thing that interests me when you talked about AI co-design, for those seed-based design that you talked about, are you only looking at the structure of the drones, or are you actually also looking at in terms of other operational data for the drones also into your model? Or is right now it's just a design optimization, looking at the architecture sampler that you referred to?
Yeah, so we are looking at so for example, if you have performance based on endurance, how far can the drone fly? How high can it hover? How well can it track? So that is part of the knowledge graph that we have, that every subcomponent of the design is related to a performance measure, because we want to generate high performant designs. And at the end of the day, we have to meet the performance requirements for the specific benchmark that we are looking at. So it's not just coming up with a mechanical, electrical design, but it is designing it for the particular requirements.
Following on the other question, how do you foresee the advancement of the CPS component when you talked about, the overall goal here is to focus on reusable software autonomous tracks, right? And how do you see the bottlenecks that still need to be addressed, and where you one use case that you talked about is actually showing this so-called robustness with safety. And so could you provide some thought on, what are the open-ended problems in that area in terms of connecting the CPS?
Yeah, that's a very good question. It's a broad question. I'll touch on a couple of things. So one is basically like there is a gap between simulation and reality, and basically bridging this gap is a big challenge like that, right? So where you model the dynamics and the physics of your system, but in reality, you don't know the full dynamics. Yeah, you can have learning-based approaches to learn the dynamics, but you still have a lot of error in the model. And here, we are very sensitive to model error. And so I think that's one aspect of, the sim to real aspect. The other aspects are really like, like say we want to build safe vehicles, or we want to build safe medical devices. With vehicles, a fatal accident happens approximately every 160 million miles. So these fatal accidents, for example, are very rare. Now, then the question is, how do you accelerate the search, for rare events, because they're on a very long tail. So this is a pretty classic problem. You can say, oh, I'll do importance-based sampling, I'll have some different gradient-free search-based techniques. But I think that is the third issue is really like, in modeling like uncontrolled behavior from other agents. So when I spoke about like learning the policy of other agents, that's only good in the first part, that Formula Zero paper. It's only good as long as the other agent is in our distribution. If the other agent is out of our distribution, then I just become very conservative because the uncertainty is too large. I cannot capture a good enough a mixture of policies, that. So I think there are lots of these issues out there. We are just, trying to build something that is useful enough at this point. But to provide like strong guarantees, there is still a big way, long way to go.
Okay, let me read some questions here. Okay, from Dr. Utku Kosei, I would like to ask, what do you think about ensuring precision medicine through model-based design and digital twin perspective? I had debates with many people not believing in realizing digital twins for people for precision medicine, but there is some potential. What is your perspective?
Yeah, so I think over here, the what we are trying to learn is, I work with many directors of cardiac electrophysiology, and I'll tell you that, first of all, physicians are a different species from engineers. They think very differently. They are really like, highly tuned, professionals who can do that procedure very, very well. And they have trained for decades on that procedure. But among themselves, like these procedures, like the ones I was talking about, they're not captured in textbooks. They're really, a mix of art and science and practice. And different physicians, they disagree on very fundamental aspects with each other. They like sometimes I would have directors from 3 different hospitals: Presbyterian Hospital, VA Hospital, the Penn Hospital, and they would start arguing with each other in the lab. And I was like, wow, the existence of rotors, for example, they don't even agree on those things. So that's one aspect that, we are trying to learn what is in the brain of the physician, what is their thought process, what is their decision-making sequence, as they are doing the procedure. And that's very hard to do because these physicians themselves are very. The second aspect is that these physicians are also like, when you build a model that is guiding a physician, every time they burn the tissue, the model has to be updated. So how do you make sure that the model is in sync with the actual patient? Because if the model is out of sync, you have this mode confusion, and then the model is basically telling you nonsense. And then the physician has, so there is that skepticism has to be there. And we are also very skeptic about, but we are not cynical about the research because we can see that the physicians themselves are asking for this. And then they say, look, I'm an expert in this, but the people I'm training are not as good as me yet. So this guidance tool can really help them. So it's just finding where we can help them. We are not saying that we will take over the procedure, but we will help make the procedure more efficient, help you shorten the time for your procedure, and also provide more confidence that you have completed the procedure as required. So the patient has to undergo less, pain.
Good. So when you communicated that to 3% error in spatiotemporal, whatever the AFT example that you talked about, the reception was okay, or do you think?
Yeah, they are part of our research team. That's also finding like a good way to work with physicians. I realized early on that, as engineers, we need to be doing the science, and then we need to have a good collaboration with physicians. So when my new students come to join my team, they actually spend half the time observing procedures in the operating room. Then they come back to our lab, and then we start to build these models. And so we have to have this, immersion. We can't just say, no, I only do stuff on computer science or electrical engineering. That's why our lab is called X Lab. We are not like a computer science lab or a machine learning lab. We are really understanding the domain problems, spending a good amount of our time and energy in learning the foundations of cardiac modeling in this case, or in whatever other cases, and then sort of relating them to the kind of modeling approaches we can use here.
Yeah, that was clearly evident from all the work that you showed, and that's fascinating. And maybe continuing on, you mentioned how optimistic are in this 15% recalls for software going forward, synergizing. When we talk about all these models, complex, now LLMs is taking over, and not sure how that's how we're going to see this deployments, and how do you see real-time learning for running complex models? You talked about NVIDIA's thing in one of your slides. I'm just wanting to close the webinar by for students who are listening, some final thoughts on some takeaways from this presentation for them to join.
Yeah. So I think first of all, these are very challenging problems, but we are making progress in, say, like, building personalization. Say, like when you go to Amazon's website, they are personalizing it to or Netflix. So here the device, can be personalized to the actual patient. Right? So personalizing those algorithms to tune to have better accuracy and better therapy. So that is one direction. The other is really that, a lot of our research is now going into the operating room, and it is a slow process, but it is a process like that, right? I think to me, I find, working in the medical realm the most rewarding, because if the work we do can even save one patient, I would be the happiest person. Versus as academics, a lot of our work is publishing papers and writing complex things and maybe making the world more complex or complicated. But I think with medical, the goal is very clear. Can you, improve the therapy? Can you save another patient's life? And I think that keeps a lot of my team motivated.
Yeah, you see the real impact. Thank you. I think I don't see any more questions coming up. In the interest of time, also passed for 10 minutes longer, but I appreciate your time for this morning with us, and thank you so much. And you will receive a nice plaque from UND, and look forward to a collaboration to speak further to see what ways we can find to collaborate. Thank you.
Very much. Thank you so much. And I'll be happy to chat with any students or faculty going forward. Thank you.
Thank you.